Should I count down, or we're just going to go?
Yeah. Okay, or just go for it. Yeah, I think we're streaming.
Okay. So welcome to the, the preparation 1 for Calculus Test 1. I'm Joshua, who you may have met, and Daniel you probably know from lectures. So yeah, we're going to go through some of these test problems from previous years, and you'll get a feel for how you should probably go for them in the test. So Daniel's going to take the first problem.
Cool. Pen. Right. Pens. Hello, I'm Daniel, and this is pretty much my copy of Calculus Test 1, version 2b from 2008. It's the first calculus class test from your book. I've just taken that pretty much verbatim. Josh and I will alternate, go through questions. And then we've selected some more questions, just kind of random smattering from the book and other exams, just so we cover all the material. Right, so question 1. This is a kind of 2-mark question. Given these two functions, compute these two objects. So, I'll just get stuck into it. What is this object? Well, that's g of f of x. You should read this g of f of x, and it means this. Well, what does that mean? Well, I take g and I replace x. So I take the function g and I replace x with this object, f of x. So this is, f of x plus 1 to the power negative 1/2. Josh, am I on the screen here? Can you just check that?
Looks fine to me.
Cool. And then what is f of x? Well, I just plug f of x in. So this is x squared plus 4, that being f of x plus 1 to the power negative 1/2. And x squared plus 5. Good. G of f of x. The other object I'm asked to find is f of g of x. This means apply g first, then f. And the procedure is the same. I'm going to take g of this, f of this object g of x. So I just apply the definition of f to this thing. That's g of x. So not x squared, but g of x squared plus 4. And then I need to introduce g of x. So this is x plus 1 negative 1/2 squared plus 4. And this is x plus 1. Bam. So the way we'll do these questions is I'll do my one, and then Josh will come along and critique. So Josh.
Yeah, so there's probably not too much to say about this. I mean, the method was done fine. So this is essentially square of a square root is just the original quantity back. You would have to be careful if that were the other way around. The square root of a square is the absolute value, but this is fine. So this way works fine. So yeah, I can't really see anything wrong with this. It's managed to get that one right. Understood what the definition of GOF means, G composed on F. So it's all fine. I can't really see anything to critique. I guess the interesting thing you could draw from this is that it really does matter which way these two are, and that's something you'll come across quite a lot in mathematics, that the order matters when you're doing things.
I mean, maybe I should have introduced absolute values here.
No, this
you don't think so?
Correct. No, so the confusion can arise is if I take the square root of a quantity, which necessarily must be positive, and take the square root and square root, that has to be the original quantity back, if that makes sense. If you do take the square root of a square, that will be the absolute value of the quantity. So there are two different behaviors here. There is a sort of an assumption here that x going in was positive. So
okay. Look, if I would have been looking for just some understanding that at least the order, this is the order of applying these things. So even if someone messed up these questions, I would at least be looking to see, do they understand what this notation is? And if they manage to get the rest right, then that's okay.
Okay.
Cool. Your turn.
Right.
So I guess what I'm trying to say is please please try and show us you understand stuff during the exam. It's nice to have the answer right, but try and show us you understand
Yes.
things as well.
If you jump from here to the very last stage, well, I guess you must have understood to get that.
Well, that'll have us scratching our heads. How did he manage this? Yeah, we like to see some understanding in the exams, but you're also limited by time, so you have to balance these factors.
Alright, so while I wait for that to dry, let's just take a look at what the next problem will be. So we want to find the limiting behavior of this function. So the function here is given by the ratio of these two quadratics. And I want to know what's happening as I approach 2. Now, the behavior could be simple, although I probably don't expect it to, but let's just quickly check what happens to the top and the bottom as we approach 2. So as we approach 2 on the top, we get a 4 minus a 10. 4 minus a 10 plus a 6. That is 10 minus 10 is 0. And this one, well, you get 4 times 2, so an 8 minus a 5. Did I get that right? No, an 8 minus a 10. 8 minus a 10 is minus 2. You hit the plus 2, that becomes a 0 as well. So, well, we can't just look at what happens when we plug in the values, because this isn't defined at 2. So we're going to have to do something different. I think this is dry now. But looking at that, I now know that the top and the bottom do have roots of 2 in it. So I can say, I know, well, let's just rewrite. Let's start out by writing what it is we're considering. We're trying to look, as x approaches 2, the limit of x squared minus 5x plus 6 over 2x squared minus 5x plus 2. And because I had a little look at it, I know that these two have roots of 2 in it, so I'm going to write this as the limit as x approaches 2. Please don't forget this part of x minus 2. And let's see, so I need another linear factor here. It'll start with an x and it'll end with a minus 3. And you can double check that's correct. Next one, well, I know it has a factor of x minus 2. Let's just be careful here. It must start with a 2x and it must finish with a minus 1. And we can double check that's right, just check the middle term. So you'll get a minus 4x and a minus x, that is minus 5x. So this is correct. Now, I'm not really concerned about what's happening at 2 because it's not defined there. But as long as I'm sort of approaching 2, so not quite at 2, then these will all just be numbers and these two will cancel out. So those, yeah, so we'll get that this is going to be the same as x approaches 2 of x minus 3 over 2x minus 1. And in this case, this approaches a non-zero number. This approaches, well, it approaches a number as well. But the important thing is this is non-zero. And there's a theorem that tells me I can just plug it in now. So this becomes 2 minus 3, so minus 1 over 4 minus 1 is a 3. So I find that this function, as we're approaching 2, it approaches 1/3, minus 1/3. So comments, Daniel?
This looks fine to me. Yeah, the important point is to realize that it's not actually defined at x equals 2, but you can look at its limiting behavior around 2.
Okay, if I wanted to make it a little bit clearer for whoever's reading, I guess.
I think this is clear. I think this is the appropriate amount of work, and look, it's really just 2 easy marks as far as I'm concerned. If I was marking this and I'm writing up a marking scheme, I'd say, yeah, 1 mark for getting the right answer, and 1 mark for knowing that something is going on at x equals 2 and kind of handling that appropriately. So I can see Josh has cancelled away before trying to evaluate the function at 2. It's fine.
Okay.
Good.
Just be careful of this term here, because that's a common source of mistakes. 2x there.
With factorising?
I think a lot of people may just concentrate on the last term, forgetting that it begins with a 2x squared.
Oh, okay, yeah.
So I can see a lot of mistakes creeping in there.
Also, you can ask us questions in the chat if you like. Josh and I are monitoring the chat, so if you want something explained or you have a request, just put it in, and we'll pick it up. Except for requesting frogs, I don't know what that's about, so I'm going to leave it. Okay. For this thing. So I guess when Josh and I are doing these problems, we really want to put our kind of, we want to take off our lecturer hats and put on our math exam hats. But for this question, I can't resist. I need to explain what's going on. So first I must say, what is f of x? Well, the first thing I do is try and get a handle on what's going on here. So since Alright, this is a parabola, and I know that it's going to be negative it's going to kind of dip below the x-axis between 1 and 3. So the absolute value is going to be, I want to get rid of this absolute value. So I'll say this thing is either equal to negative and if x is outside this range, then the function's already positive and the absolute values just drop off. Good, so this is the function absolute value of that polynomial. And the function f of x being equal to absolute value x squared minus 4 is then either equal to and now, as with Josh's previous question, I can do some cancelling. And otherwise. So good. Now I've got a kind of proper handle on this function f of x. Here's kind of, I need to unpack this a little bit before I can really start saying what's going on. Here is a version of f of x that I can actually use. I might get rid of this stuff. And maybe I should do a little sketch just so we see really what's happening here. So between 1 and 3, so that can be 1. Between 1 and 3, I've got negative x plus 3. Negative x plus 3, so that's negative x plus 3. So So I don't know what's happening here. Negative x plus 3. And for values outside this range, I've got this one. I should really not be saying otherwise. I should be saying x greater than 1, or because the function is not actually defined at x equals 1. So this is what f of x looks like. Good. And we're asked, you wouldn't need to necessarily draw a picture to go with this. We're asked to find the limiting behavior as x approaches 1 from below, above, and then at a. Well, it's pretty clear from my picture what's happening here, but I will now just, once you've got a handle on what f of x is, you can just omit the picture if you want to, and just say that lim as x approaches 1 from below first? Yes, below. Well, that's equal to lim x approaches 1 from below. Now, what is that? I have to look at my definition. It's x less than 1, so this is just the function x minus 3, which is equal to 1 minus 3 is minus 2. And from my picture, I can see that this is approaching minus 2 if I take x values less than 1. I also have lim x approaches 1 from above f of x, and this is equal to lim x approaches 1 from above of, well, I have to check what f of x is. I can see 1 from above is in this range, so it means negative x plus 3. And as x approaches 1, this is minus 1 plus 3, which is positive 2. Positive 2. Good. Now I can say that the limit doesn't exist. In order to have the limit at a point, the left-hand limit must equal the right-hand limit, but I've got a left-hand limit of negative 2 and a right-hand limit of positive 2, so since negative 2 is not the same as 2, which is then which is 1, then the limit doesn't exist. Josh?
Yep. So I quite like the way he managed to get this nice piecewise definition, so you just explicitly see what's going on with this function. So this is quite good. Well, the picture is not essential, but it is essential to do it for you, I think. You should really, if you have time to maybe make a sketch, get it clear in your mind what's going on. If you're going to make a mistake in the next 2 steps, your picture will help you pick that up. So I do recommend making a picture, even if it's just a rough one. Guess there's a typo here. You left out the f of x.
Failed. F of x.
Other than that.
Alright. Yeah, look, the picture is not necessary, and you're under real time pressure in the exam. I would actually recommend you don't draw the picture, if only because it takes time to figure out what's going on around here, and it's not relevant. What I'd rather you do is spend your time actually figuring out what f of x is. And you don't need to have the picture to then do this stuff. You just look, oh, is negative x approaches 1 from below? That's over here, and therefore I need this. X approaches 1 from above, I need this. The picture is nice in terms of explaining to you what's going on, but for your exam, I recommend is what you've got 20 minutes, 5 questions. You've got 4 minutes. You don't have time. You don't have time. So do this at home when you're practicing, but when it's exam time, do this.
Okay. So there was one question in the chat, but I think it managed to be answered. But just for anyone else who was wondering, someone was asking, why didn't I divide this by the power of x squared? Well, this isn't x going to infinity. This is x going to 2. So if x is going to infinity, that would be the right technique, because this term would be the dominating term in that. So make sure you're doing the right sort of questions. This is at a finite point. Someone else asking if we're only doing 5 questions. In fact, we're going to be doing 9 questions.
10 questions.
Well, yes. So.
Yeah, and you know, the question, how long does it go? It goes till we're done.
Yes.
So, yeah.
So until we finish.
Right. But it is recorded. So if you can't take it all in one sitting, then just come back using the same link, and it will still be there. And you can just pick up where you left off.
Okay, so question 4. We're going to just, well, this is a very simple one. You have an inequality here you would like to solve. Would you like to describe all the points x which satisfy this inequality? Still a little bit wet, but I'll try my best. So firstly, I think, I'm just going to restate the problem here. So we want to consider the inequality where the absolute value of 2x minus 3. That doesn't like that. So we want this to be less than or equal to 1. Well, that is the exact same statement as wanting this quantity inside here to be greater than or equal to minus 1, or less than or equal to 1, which is a little bit easier to see, I think. Now, I can play with both of these inequalities at the same time, so I'm just going to take, if I just add 3 to everything, all these numbers will shift along and keep the same order. So I'll get this plus 3 is 2, this plus 3 is just 2x, and that has to be less than or equal to this plus 3, which is 4. So all I've done is sort of taken these 3 numbers, shifted them along, their order doesn't change. And now what I want to do is really divide this by 2. 2 is the positive number, so it shrinks the numbers closer together, but it doesn't change their order. So there'll be a slight issue if this was a negative number, but that's not a problem here. So in this case, if I just divide everything by 2, this will be equivalent to 1 being less than or equal to x, being less than or equal to 2. And that's really all I want. I guess if I want to go a little fancy, I could say hence x, the numbers that satisfy this are in the set 1, the interval 1, 2, including the 2 endpoints. Maybe let's show our usage of this set notation, interval notation. Okay. So yeah, I think that's all you need to do for this problem. It's a very easy, short question.
Just give me a sec. Okay.
Mistake.
Cool. No mistake. That's pretty solid. I like it. Some people will choose to square this, by the way. I see that a lot. Be very careful with that. The only reason this works, squaring it will preserve the inequalities because this is actually bigger than or equal to 0 as well. So when you're given an inequality, you can solve it by squaring it, provided that you have the absolute values there. So for absolute value questions, yes, you can square it and then use the quadratic formula to figure it out. Josh's method is smooth and involves no quadratic formula, so I like it. But be very careful. If you do try and square it, just to preserve that inequality. For example, if I have like negative 2 is less than 1, I square that, I get 4 is less than 1. That's no longer true. So you do have to insist that there is a 0 there if you're going to try and square things. Yeah, looks good.
All right.
I see someone in the chat saying that Epsilon-M proofs are not tested for 1141. I don't agree with that. I think that's dangerous thinking. It's certainly on the syllabus. So do not lull yourself into thinking that Epsilon-M proofs are not on your class test. In fact, we'll do one later on in the stream. Anyway, I'm on question 5. Find the maximal domain and range of this function. So let's just talk about the natural log. Okay, just the natural log is the restriction here, because you can only have the natural log of a positive number. So the restriction is that the domain here must be positive, and I've said that here. So since the domain must be positive, you have to restrict this. This bit here has to be greater than 0 by virtue of the log function, so my restriction is x squared greater than 5. I can solve that. X squared greater than 5. That means what I'm squaring is either bigger than root 5 or less than negative root 5. As for the range, well, let's just think about what happens here. If x is bigger than root 5, then this is going to be positive, but any positive number. So my range is just all of R. And if you have time in your exam, by the way, I don't recommend that you necessarily do this, but I spent a lot of time in my exams drawing pictures. Root 5 minus root 5. Y, x. What it looks like. So you can see from the picture its range is all of R, and I have to restrict myself to x being bigger than root 5 or less than negative root 5. Josh.
Okay. Yep. So it's a good start to identify what part of your function is the problem. And here the problem is what's going on with this thing inside the log. So yeah, it looks perfectly well defined as long as that thing was positive. That thing's positive exactly when this holds. And well, for this part you just need to understand the log function. The log function takes all the numbers from 0 off to infinity to all the real numbers. Yeah, so you manage to get to all real numbers, so you get down as far as you want, up as far as you want. Yeah, so that just comes from you understanding these functions. So you should have a good feeling for what these functions actually do. Okay.
Would you assign a mark for the range, or would you not care so much about the range here? I mean, it's a 2-mark question, so what would you say are the 2 important parts here?
Because the question does explicitly ask you for the range. So
I think that this is worth a lot more than that. You actually have to do some computing here, so I'd be tempted to say, maybe half a mark for range or something like that. I feel like this is not worth a whole mark.
Yeah.
There's no stuff you have to do.
Well, you do have to understand, but
okay.
Unfortunately, there is only 2 marks here. So how they fall, potentially I could just give.
Yeah, I
one for that.
I see what you mean. Look, if someone's going to have to mark this and have to mark a lot, it's probably easy to say, do they have the domain? Yes. All right, 1 mark. Do they have the range? Yes, 1 mark.
Yes.
All right. Good. Next question. Where did we? Oh, there it is. All right.
Should we do the
Oh, you want the bonus question now? Okay.
now
bonus
or
question.
at the end?
No, let's do it now.
Let's break it in the middle. That way. So we've got a lot of requests for this particular question. especially because well, the video for it seems to have gone missing. So we're going to re-record it.
I'm sure we made
now.
a video for this somewhere.
Yes, but I can't find it.
Okay.
So to save time, I'm going to do it now, try and record it and put it up for a permanent record. So, I should. Okay. So actually, I'm going to slip a memory card into this camera.
Do you have a memory card?
Yeah.
Sweet.
Yep, plenty of space.
Yeah.
And recording.
We're not finished. Josh is just putting a thing in the memory card in the camera.
That way I can have a nice record I can edit later. So if you see this video online later, you know when it was recorded. I might also change my presentation style because this is going to be taken out of the context of the live stream as well. Alright, so today I'm going to show you how to solve this problem. So we want to look at this limit here as x goes off to infinity. So, well, I guess let's just take a look and see what the behavior is like. So we see that this term here, well, this term is growing to infinity. And this term, well, this term is going to negative infinity, which doesn't actually really tell me much because anything could happen in that situation. So really we'll have to do some work if we want to convince ourselves that this really is a zero. Why do these things really cancel out as we head towards infinity? And there's a lot of things that can happen in this situation. So, well, there's a nice little trick you can do for this one. So there's a nice way you can actually simplify this, and you may have actually encountered this sort of trick before when you're trying to like take a fraction and rationalize the numerator. So actually the same trick here is useful, and the trick is to multiply this by 1 and a very fancy 1. So to start, we're looking at the limit as x approaches infinity of just the square root of x plus 1 minus the square root of x. So I can't really do much with that. That's the way it stands, but what I can do is I can multiply this quantity by 1, and the fancy one I'm going to use is to multiply it by x plus 1 plus root x over the same thing. So in some sense I haven't changed this quantity. All I've done is multiply by 1. Now, so this is sometimes called the conjugate of this. So what's nice is that if I combine these two quantities, if I just multiply out together these conjugates, this becomes the limit as x goes to infinity. Well, you get the square root of this times the square root of that. So, well, these two square roots together are just x plus 1. Well, technically it's this absolute value, but since we're heading towards infinity, I'm not really going to take that into account. I will write out these middle terms explicitly. You have a minus root x times a root x plus 1 plus a, let's see, that was a minus root x, and then we get a plus root x plus 1 times root x, and then finally root x times root x is just x. Again, we're heading off towards infinity, so these terms are positive. So the nice thing is, these two cancel out, which is very nice, and the bottom two, well, the bottom one is actually nothing really there. It just becomes x plus 1 plus root x. So, let me just actually rewrite that, just so I can see clearly what's going on. On top, what do I have? Oh no, I made a mistake. So this is a minus root x times root x. This is a minus x, which is important. Because now when I sum these two terms together, you see there's x plus 1 minus 1. That is 1 over the square root of x plus root x. And well, this is two positive terms heading towards infinity. They'll also tend towards infinity. 1 over something heading towards infinity. Well, that just tends to 1. So in that case, I can see the limit is just 0. Now, other questions you do may not have this special structure. Other questions, you may end up with some other behavior left over in the top. Here I just had a 1. So. Okay. Anyway, so thank you for watching, and now we'll go back to the live stream. Yeah, sorry, I'm just adding a little bit, so we can cut that out later.
The stream continues with, yeah, don't thank them for watching yet.
Okay. Any comments about this one, though?
It's perfect.
Yeah.
It's just knowing that to do that trick. I personally don't like this question very much because it's impossible until you see the trick, and then it becomes trivial. So now you've seen the trick.
Where's the black cloth?
Consider this function on the interval. I must draw the picture. So it's negative sine. That means it goes like this. Does f attain a maximum on this interval? So to use the kind of theorem associated with this, you need a continuous function on a closed interval. So f of x So here I'm being a bit cheeky, and I'm taking the open interval, where's my open interval? Up there. Taking this open interval and I'm closing it by introducing the endpoint. So I can apply the theorem and say, it must attain its maximum. And in fact, I can say that's f of negative pi upon 2, which is equal to 1. It attains its maximum. Happens to be at an endpoint, which is not a coincidence. But this endpoint's not in here. Only place does it attain a maximum? So f of x on. Right, so that's a lot of words. Hopefully I haven't run off the back of the bottom of the screen. So I use the theorem to tell me it does attain. I've got to demonstrate I know what the theorem is. The theorem says continuous function. So as a marker, I'd be looking for this word on a closed interval. The theorem says if you have a continuous function on a closed interval, it attains its maximum. However, the place where the function does actually attain its maximum is not in this interval. It's here at this endpoint. which isn't an element of my open interval negative pi on 2 to pi on 2. So my function doesn't attain its maximum on this open interval. It gets close to it, gets real close, but it doesn't actually get there because pi on 2, negative pi on 2 is not in the open interval. Josh?
Right. So I feel like there is also a way to answer this question without having to use this theorem.
Mm-hmm.
I feel like the other way is also if you can, I mean, because we know where the problem is. The problem, as you've already seen, is because of this f of minus pi on 2. That is 1. So I feel that I mean, this is a good one, I guess. It does show you, the maximum is here, but that's not included in this interval. So you just don't get to that maximum. And because it's actually a continuous function, that's one of the reasons you get arbitrary. You can get as close as you like, because it is a continuous function. It has to approach that point there. So that means if you get a little bit closer and a little bit closer, you're getting closer and closer to 1, but actually you never reach it. So that's actually another way I would think to answer this question, is actually to discuss that the fact that you know that, for example, just restricted to the interval, you know that it goes between +1 and -1, and you can discuss how as you approach minus pi on 2, the limit does tend to, the limit of that does tend to 1, because this function is actually continuous everywhere. The sine function is a continuous function everywhere over the real numbers.
Yeah, I was deliberately trying to avoid any kind of limiting argument.
Right.
Look, there's probably lots of ways you could answer this question. If the question's about continuous functions, and if you're able to demonstrate you understand what's going on, then you get the marks.
Yeah, at some point in the argument, the continuity comes into it.
Yeah. Yeah, I kind of like this, if only because it avoids limits. And
Oh, nice.
cool.
Okay.
I mean, it shows you know where the function attains its maximum, but that is not in the interval. So if you can get that across, then that's what's worth the marks.
Okay, so the next question wants us to use the intermediate value theorem. And if you're not already aware of the intermediate value theorem, you might want to look this up in the notes. I guess it should have been covered in lecture. So what we want to do is use this intermediate value theorem to show that this polynomial definitely has a root between 0 and 1. There is some number I could plug in here between 0 and 1, which will make this polynomial equal to 0. I make this evaluate to 0. Well, the fact that they're telling us 0 and 1 means we probably should consider what's happening at 0 and at 1. So let's see. So firstly, let's just consider the hint they're giving us. Let's consider what happens when we look at P0. Well, all these terms evaluate to 0 except for this last term. So end up with 0 plus 0 all the way up and a 3. So the function, this polynomial starts at 3, and if we move over to 1, we find that it will evaluate to, I hope I'm not off the board, it will evaluate to 1 minus 2 minus 3 plus 3. Well, 3 plus 3 is 0, but 1 minus 2 is minus 1, which is good because that's what I want. I have this function and it's going from 3 to minus 1. Now, to use the intermediate value theorem, there are a few conditions you need to make sure are true. Firstly, the function has to be continuous, but polynomials are always continuous, so let's state that. Since polynomials, in this case all polynomials including this one, are continuous over R, over all real numbers. Well, in that case, it's definitely continuous over a subset of that, 0 to 1. since it is continuous over R, P of P, this polynomial P will be continuous, I think I'm a little bit lazy with my notation, continuous over, well, actually all I really need for continuity is that. No, actually, for continuity I need the whole interval. Right, so this function is continuous over 0, 1, it starts at 3, goes to -1. So I'll also say it this way, that since 0 is between P of 1 and P of 0, which is to say, I mean, yeah, since it's between this value and this value, the intermediate, actually there's a much nicer way to write that up. A much nicer way to write that up is, since 0 is in the interval given by P0 to P1, then there is a value C in 0, 1, such that P of C equals 0. And I'll just draw a sub-conclusion, i.e. P has a root in the interval 0, 1. Right, so I think, yeah, there were two. I know what I forgot to do. I forgot to state exactly why this is working. So since I already said it's continuous and 0 is in this range, I really should have mentioned that the intermediate value theorem tells me there is a C in between 0 and 1, such that P of C is 0. So I know there is a root there. So
Yeah.
Any comments, Daniel?
If someone wrote this and didn't write IVT, it would be clear to me that he knows what the IVT is and he's applying it. If not by name, then at least knows it very well. So even if you didn't write that, I'd read this and know this person knows the IVT and he's using it.
Well, yeah.
So and the question even says use the intermediate value theorem. So I'd find it difficult to demand that you wrote that in order to give you the marks. If I was doing this, I'd say I'd assign a mark for this, just knowing, because you know the procedure. You know you need something above 0, you need something below 0, and then you need to know that because 0 is in this interval, then IVT. Yeah. So I'd be looking for this, and then some kind of demonstration of an understanding of the IVT, because Josh is saying it's continuous, and therefore there's an element in this interval. I know just from reading what he's written, he understands the IVT well. So cool. I'd have no difficulty in saying this is a good answer.
Yeah, I would. If I was marking, I would demand the continuous statement.
Really?
Well, if you give him a function,
If someone wrote this, would you say 1 mark?
Since P, well, they wrote since P is a polynomial.
Oh, well,
I would consider that, yes.
maybe this then. Would you say that's? Will you say that's a 1 mark answer?
It's still got continuous. Yeah. No, if you luckily I'm not actually taking any classes in calculus for the students, but I would demand continuity to be stated. Yes, we all know polynomials are continuous, but you have to understand that that's just us being kind. That the function we gave you is continuous.
Okay.
I feel you should recognize that. It's a very important part of the theorem.
I accept. All right.
Okay.
Next question.
Yeah.
Okay. Use the pinching theorem to find this thing. Well, pinching theorem means you have to have two functions, both one above, one below your f of x, if you like. This thing. Where am I? This thing. And they both have to kind of pinch the function. So, let's say g of x So here's my three candidate functions. Again, a picture, I must have a picture, is y equals h of x. I can do in purple the next one. And then in between, I've got f of x is x sine 1 on x. Now sine 1 on x is doing all sorts of crazy stuff as x goes small. In fact, this function is not even defined at x equals 0. But it can go, whatever it's doing, it's going to have to be kind of between these things. That's the idea. So this is the setup. This is the setup. So you have to start along the lines of since -1 1, and then I multiply both sides by the positive number absolute by x. So I can multiply this by just say -x. X. And what next? Then this is my this is my g of x, and this is my h of x since lim. And the idea is as x goes to 0, this thing's going to 0, and this thing's going to 0. So limit as x goes to 0 of g of x equals 0, which happens to be lim. I don't really need. Let me call it negative absolute value x. And lim x goes to 0 of absolute value of x. So this function and this function are squeezing x sine 1 on x to 0. By the pinching theorem. I should mention that these things have to be continuous functions as well. So plus or minus absolute value of x is continuous. That being part of the pinching theorem. You need to sandwich x sine 1 on x between continuous functions. Then by the pinching theorem, this thing is equal to 0. Josh.
I wonder if continuity is strictly necessary. I think you really just need that these limits do exist.
Really? Do I not need continuous?
Well, in some ways, this is almost telling you that these are continuous there, although it's not taking into account the value at that point.
Yeah, the value at the point.
Although in some sense, this is all about limits. Limits never look at the value at the point.
Maybe I don't need continuous. Let me check that.
As long as it's, I believe if I'm correct, as long as you're bounding it from below and bounding it from above, and these have limits that squeeze into the same value, that come into the same value, then yes, this limit will exist.
Cool. They do not need to be continuous. They just have to have this property. So I don't need continuous. I just need this property that my functions, the limits agree at x equals 0. Good. So I don't need that. Good.
So, I guess, yeah, if I was looking at this test, firstly, I'd be very, I'd be very happy to see that you start like this. Clearly, if you write this, you clearly understand, especially with these absolute values, making sure that this thing is staying negative, that it's staying below sine 1 on x. It would be very easy to make a mistake and only have it work on one side of 0. So this is sort of a good choice, good explanation of why these bounded. And then, yeah, for this last part, the limits equal, pinching theorem tells you that the limit must be equal to 0. Now, I think it's only a 2-mark question, is it? Yeah. So it may vary a little bit, but I guess this is very important, that it pinches it and it goes to 0.
Yeah, I'd demand this and this.
So I'm happy to see that, but I probably aren't awarding marks to that. As soon as I see that, I think, oh yeah, this is going to be an easy one to mark. They understand what they're doing, probably. But yeah, so this and that is very important. All right. So one last question. And so this is an Epsilon-M question. So we're not going to do an epsilon delta one. I think that's not examinable.
Epsilon delta is not examinable.
But Epsilon-M is. So looking at limits, at least for 114 it is, right?
Yeah.
Yeah. So you will have to consider limits as we go off to infinity. So there's actually 2 things you'll need to do for this problem. One is you'll need to work out the limit. If you can't do that, you won't be able to do anything else. And then once you have that, you'll need to make some good arguments to get this Epsilon-M, the formal part, working.
Yeah, but there's a kind of structure to the Epsilon-M problem. So we'll show you the structure, and you'll just have to make it fit.
Yes. Right. So the first part, let's actually work out what the limit of this function is as we head off to plus infinity. So, right. So the first little statement for myself. Firstly, the limit as x goes to infinity of f of x. Well, the important thing you can probably see here is that as we're heading off to infinity, the dominating term in the top here is this x squared. It's going to be much larger than the 1. And in the bottom, the dominating term, well, is only an x squared. And these do match up, so the trick that someone mentioned before, we can divide by the dominating behavior to get a better feel for this. And look at the limit as x goes to infinity of, well, I'm just going to write, so this is the same as 1 plus 1 over x squared over 1. Have I skipped too many steps doing that? Probably not.
No, that's fine.
So this term is very well behaved. The top is just 1, the bottom is heading to plus infinity. I can see that this is going to head to 0. So this will just become, well, become 1 over 1. It'll be 1. And that's what I need to continue with the question. Maybe I'll just match the notation. Hence L equals 1. That limit point is 1. Now the next part, we want to actually find the value of m such that once we move beyond that m, we're within epsilon of this limit. So I want to explicitly get that close. I want to get epsilon close to the limit. So, well, I need to consider the absolute value of f of x minus L. In this case, we know it is the absolute value of x squared plus 1 over x squared. L was 1, so minus 1. That, well, we can bring this all together, make this x squared on x squared. So the common denominator gives me x squared plus 1 minus x squared over x squared, which is nice. It simplifies to just 1 over x squared. All right. So I want to make this quantity less than or equal to epsilon. Yeah.
I think we're missing some bits. We need to say for x greater than m.
Right. So let's think about how I want to explain this. Well, I'll explain it the way I'm going to do it. Then maybe Daniel can come along and explain it in a slightly different way. So I have used a lot of space doing that, so I'm going to have to rub out the first part where I found the limit. I can find that. Thanks. Right, so the way I was thinking to explain this is we want 1 over x squared to be less than, I would like that to be less than epsilon. And the nice thing about this is a monotonic decreasing function. This function just continues to go down as we head towards plus infinity. So yeah, I can see why we need to introduce the n. All right, so I'll just say it this way. So since 1 over x squared is mono, so it's just decreasing. So that's what the word monotonically means, just always decreasing. Well, that means if I was to pick a value, if I was to look at what happens when I have m some, yeah. So I'm looking at this. So first, if I'm beyond some point, so if I just say, let's pick some point and look at what happens beyond that, what I do have is that 1 over m squared will be less than 1 over x squared. No, sorry. Of course, the reason I pick this is because it keeps going down. So if I pick some point and keep moving beyond that, I always get smaller. So the obvious thing to do is, I have something which, once I know I moved beyond it, I'll be less than that. So the obvious thing to do is just make that equal to epsilon. So that's what I'm going to do. So this is our choice. We can take, well, I guess since I have chosen everything to be positive, I don't need these anymore. We can take epsilon equal to 1 over m squared. If we take that, then I have satisfied my condition. And that means I need to take that m is equal to the square root of 1 over epsilon. Right. So there were I saw a lot of people in the online tutorials recently. We were doing a lot of problems like this. There were a few perhaps misconceptions about, well, there's a thing where a lot of people would just put in m here, make it equal to epsilon. The only thing I would like to point out is that only really works because that was a monotonically decreasing function. The function has to be continually decreasing, so I get this. Once I have this, I can go, well, that gives me the control I need that gives me the thing I need to control this 1 over x squared, the leftover part. Right. You have comments?
Yeah, I'll have a go at this, because I've got, every time I see an Epsilon-M question, I just want to answer it in the same way. Okay. So, without having even looked at the question too much, I immediately just want to start setting up the kind of framework for answering an Epsilon-M question. And then I have to read what their question actually says and start filling in the bits. But it really comes down to what is the formal definition of a limit at infinity. Thank you. Formal definition is this. Picture. You have some function, it's doing stuff, eventually getting towards infinity. And the idea is that for any epsilon, so here's my kind of limit, here's limit plus epsilon, here's a limit minus epsilon. For any epsilon, the function is eventually within this limit and gets inside this sausage, this epsilon sausage, and stays there. So maybe my point might be here. Eventually, at this m, the function is within the sausage and stays there. So this is a game you play. Your enemy specifies some epsilon, might be small. You have to come up with the m that puts the function in the sausage. That's the game. For all epsilon greater than 0, which is some unknown thing to you that your enemy has chosen, let m be equal to something. I don't know what this is yet. I'm gonna find it. For the moment, this is the structure. If x is bigger than m, so if x is bigger than m, then my function is supposed to be close to its limit. That's my function. The function is that the limit was 1. It was 1. This thing, I'm going to bash this thing to be so that it's less than 1, and I'm going to use this to do it. So this, Josh already showed you that this was just absolute value 1 on x squared. Good. I can't have x, I can only have m. Fortunately, it's monotonic decreasing. So because x is bigger than m, this thing is less than or equal to 1 on m squared. And this is what I have to make less than epsilon, because that puts the function in the epsilon sausage. So there's my epsilon. And then I just rearrange this and I say that m has to be 1 on root epsilon. So I can, once I have this step, then I can come back and say, my enemy has chosen the epsilon greater than 0, this is my m. And this is the m that works, because if x is bigger than my m, then the difference between the function and that is less than 1 on epsilon. So this structure this is the same structure every time you get an Epsilon-M question. It's always going to be, let m equal something. If x is bigger than that m, this difference, make it less than epsilon, using this. Right, so...
I would say that maybe one thing, the hardest part about these questions is maybe finding an appropriate upper bound. Here it's easy. The function's very well behaved, no need to do anything complicated. Some functions may not be so well behaved. If there was a sign inside here...
Oh, there's not going to be, don't scare people. There won't be a sign.
Yeah.
Cool, so that's the end of the stream.
Okay.
So, any parting words?
Good luck.
Good luck. It's a 20-minute test, no calculator. The no calculator thing is more a statement of intent. You won't need a calculator for the test, so don't worry too much that you will have no calculator. Anything else people need to know? Bring pens, bring some paper.
Bring a stapler.
Stapler, yeah, good choice. Excellent.
Okay.
All right, we'll see you for the next stream.
Okay. Well, actually, next stream will be Daniel and Daniel, right?
Yeah, next stream's Daniel Chan and myself. So, Daniel, I will see you with another Daniel next stream.
Yes. And I'll see you next calculus stream.